Okay. So I will tell you something in general about Raman spectroscopy. Then some few words will be about history, and then about the spectral Raman. This is the instrument which we acquired in our center. So what Raman spectroscopy is? This is the method, instrumental method, by which we can extract the information about vibrational properties of the molecules and materials. So Raman effect is used in science, especially materials science, then in industry, where you can measure and control processes, and in remote sensing. This is extremely popular last 10 years. So you can measure the composition of the matter from 7 or 10 meters distance. Such spectrometers are useful also for space mission. And there is another application there, which is you can measure the composition of the gases in the atmosphere and also of the solid particles. So Raman spectroscopy is complementary to ear technique. But it has some advantages over it. You can use water solutions as a sample. Then the analysis is pretty fast. There is no sample preparation, no sample degradation. You can use small amounts of sample, and there are samples can be liquids, gases, or solids. So let's see some history. There is a, I will just stress the first line where when the theoretical predictions were about Raman effect, and then I would point out some commercial improvement, which was in 1964 due to the laser use in spectrometer. Next jump in commercial development was in 1974, when optical microscope was attached to the Raman spectrometer. So it was really big jump, big improvement. Next year, I would say it's 1992, where commercially available desktop instruments were available, and from that year, the number of Raman instruments increased considerably. So nowadays it's a pretty usual instrument in the lab. So here we see the scheme, how light scattered in the matter. So we have initial light, laser light excites the system to the virtual level, and then when there is a when the light is scattered, we can have a jump to the ground state or to the vibrational excited state. So we have with first one, the name for the scatter is Rayleigh scatter. It has the same frequency as the exciting radiation. And in the second one, the name for the scatter is Stokes, and the frequency of radiation is lower than the frequency of the laser. So how that would look like. This is the spectrum of the Stokes Rayleigh and also anti-Stokes radiation. So I would stress just for the convenience that for UPAC recommendation, this is the International Union for Pure and Applied Chemistry, it recommends the plotting of the Raman spectrum that way, so the frequency would increase to the left. So what information can we obtain from Raman spectrum? First, Raman frequencies are related to composition of material. Then changes in frequency are related to strain and stress in material. Polarization of Raman peak would tell you something about crystal symmetry and orientation, and width of Raman peak is related to the quality of the crystal. The intensity, of course, is corrected to the amount. So what kind of instruments we have here? There are two instruments, two different designs, Fourier transform and dispersive Raman. So Fourier transform is in principle interferometer. In order to obtain Raman spectra, you need to apply Fourier transform algorithm to the Raman signal. This type of instrument has advantage. There is virtually no fluorescence. It has extremely good X-axis accuracy, and but it is used because it's a huge instrument. It's used mainly for bulk samples, organics, and for making spectral libraries. The other type of the instrument is dispersive Raman. It can be used with small amounts of samples. Fluorescence is a problem, but can be suppressed sometimes. The advantage is it can be coupled to other instruments like AFM, optical microscope, infrared spectrometry. So if we couple Raman to optical microscope, we get quite many advantages. First is confocal light collection. So for that reason we have high lateral resolution, high in-depth resolution. Large solid collection angles would provide for strong signals. And you can use small amount of sample. This is the scheme of confocal aperture, how it looks like. So this is the spectra, Raman spectra of polymer layer, which is deposited on silicon wafer. So we see that using confocal microscopy, you can get rid of the Raman of underneath silicon, which is 520. This is the silicon 520 band. So because the depth resolution is very good, we can get rid of that band. So here I think it can be seen a little bit. I would like to show you the designs, different designs of instruments. So this is experimental Raman. It can be seen in physics labs. It's used, it occupies the whole optical table, and it's used for Raman effect study itself. So the here we have desktop or benchtop design. This is sold best for years, and also handheld devices, which really are small, quite efficient. They are used by army, by geologists. They are small, but the price is not so small, so it's comparable to the benchtop. So here we have Fourier transform benchtop spectrometer. You see it's a little bigger. It's not easy to make it small. And this is Spectra Raman. This is the instrument which was bought for nanocenter. So we have it's coupled to optical microscope. So this is a Raman spectrometer microscope. There is a video camera which you can use. Here is schematics for laser beam travel. So laser enters spectrometer through the optics and it travels to the microscope. So in the sample it is scattered, and scattered light is collected by projector in 180 back scattering geometry and sent back. So here it enters spectrometer, or it's measured when it's dispersed or grating and measured on CCD camera. This is the inner view of that benchtop instrument. It's pretty crowded, but it's mainly due to servo motors. Optical elements are not so big. So these are components of spectrometry. So you get all this, you can make a spectrometer by yourself. The parts which are marked red are moved by software. So they are controlled by the instrument. So for our instrument, we have three laser lines. So this is 785, 532, and 633 nanometers. So this is in the visible range. This is infrared. There are also four gratings. So the first one is for high resolution work, and the other one is for wide range coverage. So you can make spectrum over the wide range of frequencies. In addition, there is a cooling stage, which is Oxford instrument. It provides cooling of sample down to 2 degrees Kelvin. Detectors. There are three detectors. Two CCD cameras. One is end of 8 AM CCD, and the diagram we see is about quantum efficiency. So the working frequencies of our lasers are in this range. So we see that the CCD camera is quite efficient in this range. Another one is indium gallium arsenide camera, which is used in infrared range up to 2 microns. I think a little bit more maybe used. It's used for fluorescence. Then how we collect Raman spectra. We put simply our sample on the microstage. So it's here. This is an optical microscope, and instrument would adjust itself. Then you push a button and you get an image of the scattered light on CCD camera. So this is your first guess. So this is the image of the Raman signal. Because the camera is big, so if you use the whole CCD camera as a source of the signal, there will be quite a lot of noise. So we mark the range where the signal is stronger, and then we just take, we ask computer just to measure and use CCD pixels in this range. So with this kind of management, you can improve the signal to noise ratio quite well. So this is original, and this is a smaller range. There is also X-Y scanner, with which you can travel 7 centimeters in one or other direction. It is a mechanical one. So, but the resolution is pretty high. It's below 1 micron. So this is the video camera image in the microscope. You can mark if you have really plain samples. You can travel quite far away from here, so you can mark squares and scan square, I think 200 by 200 pixels. So you can add many of such squares, so you can scan quite a big area while you are not here. Computer does it by itself. So how that such scan looks like? This is XY, and the light pixels, the light surface is related to 1334 Raman peak of diamond. This is CVD of diamond on silicon wafer. So all these spots which are light, there is a location of diamond. So this is about all I plan to tell you. So conclusion would be the instrument, if somebody has wish to see it.
Are there any questions regarding this part?
Just a quick one.
Please.
Yeah.
So, I'm interested in the last image, which looks quite interesting for many studies. So, what is the resolution, let's say, in microscale? Like suppose you have a heterogeneous sample that is composed, not necessarily of different material, but rather, I would say, shift in the Raman bands. So, and it is arranged in space of, let's say, 5 to 10 microns spatially.
Yes.
So, would that instrument be possible to see it, like to see the variation in the Raman band on that level?
Yeah, there's definitely. So the resolution is below 1 micron lateral, so it's around 0.2 microns. But even higher resolution, there is with the next talk, LFM. That would be pretty much better resolution in that instrument.
This half micron, it's the resolution of the stage, and what's the spot size?
That's the resolution. I mean, the resolution, it depends on the objective you use and on the laser that you use. So if you have a laser with let's say 500 nanometers has a better resolution than 700 nanometers because it's, physics, that's right. So, and the second part that is important is the objective. So we have the objectives with high numerical aperture, so that means that they don't destroy the resolution. So, there are special objectives. So actually the resolution problem is due to the spot of the laser, not due to the moving of the stage.
Yes, yes. Suppose what's the spot size? I guess this half a micron is just the step in the stage movement, as I understood. Is it true? Half a micron. Half a micron is the spot size.
No, the spot size is from, I don't know, from 200 to 600 nanometers. It depends on the laser. But I will tell something about that later.
But it doesn't depend on the sample, right?
No.
Okay.
What is the maximum sample size that can be examined? Say, can I, for example, scan the surface of this notebook?
Not exactly. It should fit under the optical microscope. So that would be.
So it cannot be moved up, for example.
Well, there is some space, but you cannot bring the card.
Okay.
It's,
So we are talking about millimeters or centimeters?
there are centimeters. But on the other hand, I didn't mention that there is an option on the microscope where you can bring really big objects. So you can measure Raman from side. So there is a connection which would reflect laser light to the horizontal position. But of course, you cannot scan on the notebook. It's just a bulk measurements.
Yes, please.
I wonder how you can analyze anisotropic material. So you have some polarizers for the laser or the scattered light.
I didn't mention that there is of course polarizer, analyzer, and always automatic. Also you can turn the polarizing light by a fraction, I think 5 degrees or something like that.
On steps, like
On steps,
the
yes.
resolution, but,
So for somebody who is studying symmetry of crystals or orientation, that would be pretty good instrument to work on.
You said that you measure 180 backscattering.
Yes.
How about solids? I mean, not transfer.
About solids. So it's
Okay, but backscattering is 300.
yeah, it's so it's measured in the back direction. So it's
There is no other options like 90 degrees.
here. Of course, there is an option, but you can
Do it
to
by
work
yourself.
on it. You have to work on it. It's at the present, it's not.
Anybody else? No, thanks a lot.
Okay.
I'm Milos, and I will present you the atomic force microscopy and the combined techniques of the AFM and Raman. I don't know how familiar you are with the AFM, but here's the outline. So I will do some introduction to the AFM, for those who are not familiar with the AFM, some principles. Then I will say something about the scanning probe microscopy, about the AFM basics and techniques, and after that I will come to the combination of Raman and AFM and some special techniques here and what can we do with the system. So first, how AFM works. I'm sure you all know the optical microscope and or electron microscope. Here is one from the institute, and the principle here is similar to the reading. So we observe the samples with the light and then we obtain some images. With the atomic force microscopy, that here's one example similar. We have one of them that we have on the institute. It's more like being blind and reading like the braille writing. So this is the easiest way to explain someone how the atomic force microscopy works. But of course, atomic force microscopy is just the part of the scanning probe microscopy, which is the technique that uses the probe to scan the sample, and that the image is obtained by the nature of probe and sample interaction. We have the scanning tunneling microscopy. It was invented in 1980s, where we observe the tunnel current between the sharp metal probe and the conductive sample. They won the Nobel Prize for the STM. Then we have the AFM, where we use the probe with the tip, and we touch the sample to see the and then we observe the interaction between the tip and the sample to observe the images. And the third technique here in the SPM is the scanning near-field optical microscopy, where we use the tip with the hole in it and then we bring the light to observe actually the optical microscopy, but near to the sample. Well, I will focus on atomic force microscopy. So here is the scene, how it looks. We have a cantilever. It's a silicon chip, and then we have a probe at the end of this cantilever, with which we observe the sample. So what detection system we use? We have a laser spot on the laser that shine the light on the end of the cantilever, and then we detect the scattered light on a photodiode. And as the probe and cantilever moves, we from the detector we have a feedback system to move the scanner up and down and to move in XY direction. There's a lot of operating modes for these systems, but here is the reason for these operating modes. So we have a contact mode, non-contact mode, and semi-contact mode. All these modes come from this plot, where we see how is the force dependent on the distance between the tip and the sample. So this is the non-Lennard-Jones potential, and as we come with the tip from far away to the sample, let's say, we have this dependence. So in the lower part of the graph we have attractive forces, and in the upper part we have repulsive forces. So when we come close enough, there's an attractive force between tip and the cantilever that brings and the sample that brings our tip closer to the sample. But if we go too close, there's a repulsive force. So three modes are the contact mode, where we are scanning the sample with the tip on the sample. The second mode is the non-contact mode, where we're scanning actually not in the contact, but we still feel some forces between the tip and the sample. And the third part is technique is when we're oscillating the tip and are just touching the sample in points. Here, what I can mention is that also in such a geometry we can measure the scanning tunnel current. So actually we have also the STM in the AFM system. So here is the movie how these work in the semi-contact mode. So that means that we're oscillating the tip, and when we come to the edge, we see that the amplitude changes. So we need to modify the height, and we then measure the distance, the changes in the distance of the sample. And of course, if we have, as we saw here, we play it again. If we can also observe the difference between two different kind of sample, because there's a different interaction, and we can observe that here it will change the amplitude of the tip. So here is the list of the different modes that can be used. I won't stress everything because it's more than 30 possible modes, but all these modes have a special requirement, and this is the need of a lot of different tips that are quite expensive. So here are some examples of these tips. So I will just show some pictures because they're really different, and they can be, so we need them for different modes. But of course we can use all these tips with the coating that then can do, let's say, magnetic force microscopy. We use the same tip. They look the same, but they have different coatings to obtain this data. What else can we do with the AFM? One thing is the AFM spectroscopy, where we measure different quantities like force, current, amplitude, phase, or frequency changes as a function of distance. So here is the plot, how it looks. This is we have cantilever and tip far away from the sample. Then we bring it closer, and in the point when we touch, so here is this point, then we start to approaching more, and we see that then this cantilever bends. And when we go backwards, we see the same, the similar behavior, but when we come to this point, we have sometimes the sticking between the sample and the tip, so we have this jump. And from this we can obtain forces and frequencies. And then when we are retracting more, there's no change in cantilever deflection. So and what is interesting is many pass techniques. This is techniques where we use at least two scans. Here is the presentation. So first we do the topography scan. So we obtain such a curve, and in the second scan we remove the cantilever and the tip in this shape of the topography, and then we measure different signals. Here is the signal of electric force microscopy. This is the techniques that is used for imaging electric fields and electric charges distribution on the sample. We can also observe the magnetic fields distributions. Of course, we need a special tip, but we can observe the magnetic domains in samples. Then we have the similar thing for the capacity measurement and for the distribution of surface electric potential. This is the Kelvin probe microscopy, which is quite interesting and also useful. What else can we do is the AFM lithography. These things are not so maybe important, so I will just briefly tell that we have a contact force lithography where we are actually with the probe we are scratching the surface, and it has some applications in nanoelectronics and nanotechnology. And we have electrical lithography where we apply the potential between probe and the sample, and it can cause modifications of the surface, and also has applications in nanoelectronics. And here is the example of such an electrical lithography of Marilyn Monroe on a, I think, gallium arsenide substrate. So now I will come to the combination of Raman and AFM. Here's the system. Here's the, you already know this part. Here is the part with the AFM, and this is the spectrometer that is used. The location of the equipment is in shelter. I don't know if this is Zaklonište actually, so, but we will go there later to see the equipment for those who are interested in. Why we want to combine AFM with the Raman? Of course, we get the positive things of the AFM and of the Raman, and some extra things. So we can observe all the things that we can observe with the AFM and with the Raman, but then we can have this tip-enhanced Raman spectroscopy or microscopy, and we can have also confocal fluorescence, and this is the small, so optical microscopy. Here is the how this setup is done. So we have an objective, then we shine a laser through this, and we have a IFM or STM probe enclosed of the sample. So what we can do, we can obtain AFM images and Raman images. So we can do the mapping, or we can do this tip-enhanced Raman spectroscopy. That is actually very interesting because of the resolution that we can obtain with this system. Because Raman resolution is limited because of the optical limitation, and what we can do with the tip-enhanced Raman, we use a metal probe. So we bring this metal probe close to the sample, and with this probe we enhance the Raman signal, and the resolution in principle it can be around 15 nanometers. But of course the problem is that we need very good tips. The best tips are those with that has just one atom at the end of the tip. So now I will show some pictures what can be done. First of all, graphene. This is the topography. It's 30 micron size of the image, and we can do different, let's say, cavern probe microscopy, different types of AFM microscopy, and of course at the same time we can do the Raman map, and we can extract different bands in this Raman spectra. So we actually obtain the whole set of different images and different data. What else? Nanowires, of course, are the next interesting thing. Here we have also we can obtain the optical image, but then we have the AFM image and the Raman map and the fluorescence map, and of course we can change different bands to see this different shift in Raman spectra. It can be also used in biology. This is one example of observing beta carotene in algal cells. Here we have the optical image, the confocal image, and the AFM topography. From these images, we can't say anything about the carotene in the cells. But if we obtain the Raman map at the same time, then here we see this Raman band in the spectra, and we can just extract this part, and we see the distribution of the carotene in cells. It can be also used for the polymer blend. We have, let's say, a blend of polymer in the AFM, and then we obtain at the same time AFM and the Raman images, and we see the whatever. It's interesting for us, and nothing can be done without the carbon nanotube these days. So here is the example of the TERS, how we can improve the Raman spectra if we use the tip-enhanced Raman spectroscopy. So here is the Raman spectra without the tip, and when we bring the tip close to the surface and obtain the same spectra, we see that there is some big increasement in shifts, and we can also see some in peaks, and we can also see some peaks that we don't see if we don't use such a system. But as I said, very good tip is a problem too, but it can be done. But we need to repeat this measurement several times. So here are the conclusions. We saw the working principles and some operation modes in the AFM. Then what are the good sides of combining Raman and AFM? Something about the TERS and what can be done. So if you have some questions, here are the contacts. If I cannot answer all your questions that you have now, but later after that we can go to the laboratory to see the equipment and to talk about it. So thank you.
Milos, thank you very much. Do you have some questions right now?
Yeah.
Yes.
What is the lifetime of the tip? I mean, you destroy the tip, then it's scanning for...
Yes. I mean, that's depend on the kind of tip you use, and of course the kind of samples you use, because some samples, all you ever want to have the sharpest tip as possible, but you can destroy the tip. You can pick some part of your sample with the tip. So it's impossible to say. You see on the image when the tip is not good enough to work with it later. So
Are they expensive?
sorry.
Are they expensive?
Yes, they are expensive.
You can't make them?
Well, you can make this STM tips for the tip enhanced, but the AFM tips, I don't know that someone will produce it, because, well, we have the focused ion beam here at the institute, so probably we can do this, but it will take a lot of time.
It's more expensive.
Yeah, probably it will be more expensive, but the price of the tip is from 20 to 50, 60 euros per tip. So, but you can destroy tip
No,
easily.
close to Raman you have also thick
Yeah.
focus iron beam, and
Yeah.
there you can cut and
Yeah.
you can prepare pieces well,
Yeah,
so maybe the wood ones can be additionally cooked.
Can be, yeah.
Somebody else?
What was the price of this machine?
It was something around 600,000 euros.
600.
Yes.
600.
Yes. Well, we have actually one additional AFM that is in vacuum, but we cannot use it in combination with the Raman. So actually there are three systems there.
Okay, but you mentioned that you can measure. You measured only at room temperature because I just did not get the connection between Raman and this because the
Yes,
was Kelvin,
the Raman and the AFM can be measured only at the room temperature.
So what was that? Okay,
But
that's general.
the micro Raman, that is also the part of the system, has the cryostat, so we can measure.
Oh, this kind of. Okay.
But in this AFM and the Raman, we can have the controlled atmosphere. So
But it's too expensive. I mean, 600,000 for this.
I have two questions. The first one, what is the typical enhancement factor that you get in this method? And second, whether you can also make measurements with the samples in liquid, so you have a liquid sample in this device.
the first question is the enhancements is around 5 and 15 times.
So 1 order of magnitude, that's typical.
Yes, I mean it can be better, but we with the tips we made here we didn't achieve it yet. A bigger enhancement. The samples in liquid of I don't know exactly if it's possible. So I mean the both AFM and the Raman can be done separately in liquid. So maybe it's possible to combine these techniques, but I don't know if we have the special head. I mean the chamber for the measurement in liquids.
Okay. Thanks once more. And